It's a carnation. I think it's my pretty flower, but it's still pretty if it's not.
Mine is a violet. And my boyfriend's is a Morning Glory, Bluebell, something like that. The ones
Oh,
that
yeah,
drip
those are
down.
pretty.
Yeah.
There's so much I need to do.
What happens when, actually, one recording?
I am.
So what happens when a wave hits a boundary?
It bounces off.
Okay, what is that called? Yes. Usually without the question mark, but yes.
Okay, got it.
No signal.
Uh-oh. I need to get a manicure. Me too. I'm getting my nails done tomorrow.
There we go.
Mine are awful.
All right, so what happens? So there's two basic types of boundaries. There's the fixed end and the free end. So what happens to the reflection when it hits a fixed end?
Does it bounce off both of them?
There's only one. I mean, a fixed end would be if you've done battle ropes before. Anyone done battle ropes?
What's a battle?
One. It's a long rope attached to a wall when you.
Oh, yeah.
Okay, that's a fixed end because the end on the wall is fixed to the wall. It can't move. So when the wave hits a fixed end, what happens?
It comes right back. The same. It doesn't lose energy.
Ideally, there's no loss of energy. We live in a nice ideal world here. All right, so I got a wave that's being sent along. If I got an end right here, that's fixed. When the wave hits it, the wave wants to keep going that way, but when it hits it, it basically doubles back very quickly. So if I send a wave, first drawing probably not the best one I should have done. If this is coming this way, when it hits the fixed end, it's gonna come back
The opposite way.
inverted. So this is with a fixed end.
Okay, that's what I assumed would happen. And then for the other end?
That's the end, that's a free end. Free or fixed, that's the end we're not as concerned with. So if I send two waves, let's stick with this. So I send the first wave, I got my fixed end here, it reflects back inverted. And then I've got a second wave coming in. What happens when the two waves meet?
They collide.
And
They do it the inverted way, like opposite.
as in they bounce off each other?
Yeah, they bounce
Yeah.
off each other and go.
No, they will not bounce off each other.
Will they collide and like merge?
Okay, and then?
And then they will become one wave.
All right, so if these two waves have the same height, or same distance from middle to end, when they are completely overlapped, when they merge completely, what will it look like? If I've got this trying to pull it that way and this trying to pull it down,
Like a big oval or something. Like it would just be one.
it is one piece of string though, so
Yeah.
are you saying that the string is going to split?
Oh, no.
It balances out.
Yeah.
flat?
Yeah, it becomes a flat. It's called destructive interference. So there will be a moment apparently it will catch up and probably erase more than I intended. I do not. Yep. All right, we'll head over to the board here. So as the two waves, if you sort of imagine, I have my top wave here going this way and my bottom wave going this way. If that's being pulled up and that's being pulled down, they do neutralize each other, and what it would appear is just a flat line. If I send a bunch of waves at the right frequency and the right speed, we get nice little patterns. So, I have this thing vibrating up and down to 60 hertz, 60 times a second. If I increase the tension here, we get these points where it's vibrating a whole lot and vibrating not at all. The point where that's staying still, because the waves are basically passing through each other and they're canceling out perfectly. They're traveling at just the right speed, the right frequency, that they cancel out right there in the middle. That is called a node. So that is a node. Oops. All right, so we have the nodes at the end. We got a node here, right? In the middle where it's really thick, where it's basically it's one string, but it's moving so quickly it looks like it's in two places at once. That's an antinode. So in the lab, when I'm asking you in table 2, number of nodes, we'll have a node at this end because that's going to be not moving in theory. And if done right, there'll be a node here. It's close to 1. Now, obviously, holding it by hand, not particularly effective. Also, if you noticed, as I apply more force, this starts moving. So during the lab, somebody might want to hold this in place. Also, especially for the 2 nodes, that's known as the first harmonic, you'll have one antinode in the middle, 2 nodes on the ends. There's a whole lot of force here, and if these aren't clamped down, they could either collapse in on itself or start moving towards each other. And we don't want that. We want a fixed distance here. So you'll be applying different masses on this. A different amount of mass, which causes a different amount of weight, which causes different tension, and that tension affects how fast the wave is going to travel. And then ultimately, you're going to see how close you get to the actual frequency of this. If you take time and care, you can get excellent results with this lab. Questions up to here? All right. Now, the biggest place that people will make mistakes. It took me a couple years before I finally figured out where the common problem was. The speed of a wave is the square root of the tension over the linear density. So let's just do a quick check here. What is density?
Mass over volume.
What is surface density?
Down here.
If you're talking about a surface, you're not talking about a volume. It's just it's something flat,
Would it be length?
not length. For a surface,
Yeah, would it be area?
area. That's mass over area. Linear density. Now comes your other answer.
Length?
Mass over length. And before I continue, there's 2 different symbols typically used. They use a lambda here, but wait, no, I did use mu, okay. The linear density is found by basically mass over length. So you'll take a really long piece of string. It doesn't have to be the one that you actually use in the lab, but it has to be the same type. So if you're using this, I might have a meter of string for the actual experiment, but I might have 3 meters of string in order to actually find the mass versus length. Because the linear density of this should be the same regardless of how long it is. The biggest mistake that I see is measuring the mass. Because the mass of this is going to be so incredibly small, which means that if the balance is a little bit off, it can completely throw off your other measurements. it can easily introduce 30% error. So that's the point where make sure I got several different variations of it. So when I'm finding the mass of the string, make sure it is zeroed properly. So when you put the triple beam balance here, everything's on 0. The line, stop. These lines should line up. If they don't, if it's a little bit above, no, wrong way. If it's a little bit below, I can add a little bit of mass here to get it to 0. Or I can adjust this. So adjust it one way, it'll move, this will move up, adjust it the other way, it'll move down.
Will you then subtract the added mass
If,
from your mass of the string?
if you put it on here and put it above 0, like right now this one is, it's above 0, so what I could do is I could adjust that, get it to 0, and then I'll subtract that from whatever the mass of the string is, yes.
Okay.
If I adjust that so it's perfectly lined up,
Then we don't need to do it.
yeah, it depends on where you want the effort. Yeah. Oh, when you are finding the number of nodes, the 3 nodes is probably the simplest one to find. 2 nodes, you're going to have to put a lot more pressure, a lot more tension on the string, so a lot more weight hanging on the end. 6 nodes gets a little bit difficult. We got this trade-off. Getting 6 nodes is a lot easier if you have a really long piece of string. But if you have a really long piece of string, getting the 2 nodes is more difficult. So it's a trade-off where you want to put where you want the pain to be. Now, as you're going through it, you might get 2 nodes, 3 nodes, 4 nodes, and then suddenly you have 6 nodes. That's fine. If you have 6 nodes, go for it. Do that, record that information under 6, and then come back and try to find 5. If you happen to get 2 through 5 and you're trying to get 6, but suddenly get 7, scratch out the 6 and write 7. So basically, you're going to get 5 data points. But 6 might be a little bit tricky. The video that I did for this probably had the most profanity cut out of it because the string broke. And it also turns out that the camera has a rate of 60 frames a second, which is the same as that's vibrating. So when you're filming it, the string doesn't actually look like it's moving at all, which was a nuisance.
That's trippy.
Yeah, like the anti-grav helicopter, I don't know if you've seen that, where the refresh rate happened to match the amount of time it took for the blade to go from here to here. So it looks like the blade's not moving at all, even though it's still spinning.
Yeah.
All right. You can assume in terms of trying to get a level line here that the windowsill is level. You can use an angle indicator also. That gets a little bit tricky. It might be easier just to eyeball it against something that's supposed to be horizontal. This is going to be the basic setup here. When it comes time to using small masses, don't feel like you have to be stuck with this. These are nice and convenient, but if I put a 500 gram mass here, make sure it's on the actual signal building. All right, it's still oscillating, kind of, it's not perfect. I can push down a little bit. Do I get better results? No. If I go up, ooh, that's a better result right there. So I need something a little bit under 500 grams. So I would take that off, put on the 400, put on another 400. Sorry, those are 200s. That's 400 right there. That's 100 there, I didn't mean to put that on there. Looks like a node there, node there, node there. Did I get better? Get slightly better. So maybe I don't want a 50 there and I want some 20s. So anyway, as you play around with that, you might get into the point, if you're being careful, that you need really small bits of mass. And that's why we have this. Pennies in small bags. So if you need really tiny masses, we have this. You can use the bags to collect it. You can see that some people have done this before you. Just once you get it perfect, you take it off, you put it on triple beam balance, figure out what the mass actually is. And I think with that, are there any questions? Then I say we should be rejoicing, because as you know, it is physics.
What the heck is this wishbone thing?
Oh, that's